Morning, everybody. So today we will talk about memory safety and security. But before that, there is one remaining paper presentation for last week, from last lecture that we want to first do that and then move on to our next topic. So let's get started with that. Share my screen. All right. Good.
Okay. Right. Hey everyone, I'm Bhavik.
I'm Jason.
And the paper that we're going to be presenting is RHMDs, or Evasion Resilient Hardware Malware Detectors.
All right, so let's start off by talking about what this paper is trying to solve. The problem that this paper is trying to address, as we learned in class, is that malware is becoming an ever greater part of our daily lives. As we go around the internet, we're quite likely to interact with multiple different types of malware, as we also learned in class, on a very regular basis. As a result, it becomes very, very vital to have this sort of multi-layer security. That way, if one layer on your system is compromised, it becomes a lot less feasible for your system to be completely compromised and vulnerable to attack. As a result, people have recently proposed using these things known as hardware-based malware detectors to provide this additional layer of security to protect your system. The name HMD, or hardware-based malware detector, is actually a bit deceptive. Note that it's hardware-based, meaning that it's actually software, just that it uses hardware characteristics to be able to identify malware. So the hardware-based kind of makes it seem like it's based on the hardware, it's like implemented in hardware. However, it's actually software, and it's actually used in machine learning networks. So what HMDs essentially are is that they use these hardware features to create neural networks or machine learning models to be able to classify something as malignant or benign. We'll talk more about how that works later. So while HMDs are a very, very promising new entry to this field, they have their own set of issues. So one very, very key issue with HMDs is that they can actually be quite easily reverse engineered. So through some sort of process that Bhavik will elaborate on later, you can actually kind of obtain a very, very similar model to what an HMD is like, even if the HMD is kind of a black box, they're not able to see the internal implementation. Once you kind of obtain that similar model to the HMD, you can actually use it to fine-tune some sort of thing known as an evasive malware that is capable of slipping through that HMD. You can think about evasive malware as malware that looks like a normal program to that HMD. And as a result, the HMD is not very likely to be able to classify it correctly. So with this problem in mind, it becomes very necessary to create some sort of resilient HMD that is both capable of not being easily reverse engineered and is also capable of dealing with evasive malware. So now that we've talked about the problem, let's go into a deeper dive into what HMDs are and what they do. So as we mentioned earlier, HMDs are machine learning models that are trained on this hardware data. The hardware data is specifically known as hardware performance counter data, or HPC data. So what HPC data is, if you take a look at the diagram on your hardware, I guess, it records a lot of useful information about the hardware, such as CPU cycles, branch hits, TLB stores, cache misses, and from that, you can kind of take all that data, aggregate it into different categories. For example, you can have one category about instruction mixes that talk about which instructions occur most frequently. You can have one about memory accesses. You can have architectural related categories. So once you aggregate them all into categories, you can begin to train your HMD model on this sort of data. So the HPC just records this hardware-related activity in a set of registers that are implemented on the chip. So one issue with HPCs is that they're actually quite new and they're also quite expensive. For example, the high-end Intel Xeon chip only approximately has 6 registers to hold all this HPC data. As a result, it becomes very, very important or vital, in fact, to identify issues with HMDs before we try to go about implementing HPCs on every single modern device. So even with HMDs, you can actually have many sorts of types of HMDs. They use many different models. For example, if you look at the diagram on the bottom, you have all these different models, based-net, naive-based, logistic, SGD. They're all capable of being employed for an HMD. However, what these HMDs all have in common is that they either return malignant or benign, depending on what program is currently running and what input they receive. So with this in mind, let's talk about how an adversary will be able to attack these HMDs.
Okay. So the first thing that I'm going to talk about is not really an issue that's specific to HMDs, but just machine learning models in general. So if you guys aren't too familiar with machine learning, at a very high level, what it is there's some input vector that is put into the system. And inside that system, kind of hidden from the public, is a bunch of weights that have been optimally trained in order to identify that input. And then the weights and the inputs will kind of do some math together and spit out an output. And in this case, for HMDs, that'll be like a classification for the malware is either benign or malignant. And so in the top right, you have the diagram of exactly how these kind of models are reverse engineered. So the victim model is kind of a black box, so we can't look into it right now. But what we can do is we can query inputs to that HMD and we get out the outputs. So we can put in our training data or our input data, a bunch of benign programs and a bunch of malignant programs. And what we get returned from the victim HMD is whether the HMD classified that as malignant or benign. And then we can create our own model and train it on that data in order to try to mimic the victim HMD as well as possible. And even if we don't know the exact type of model that the victim HMD uses, we can kind of just try a bunch and kind of see what works the best at approximating the behavior of the victim. And so classifiers specifically are super easy to reverse engineer. And another example, because this isn't limited just to HMDs, but another example about how this can kind of break and how is a security flaw for other machine learning models is for ML as a service providers. So for example, like AWS, Microsoft Azure, if you guys are familiar with that, they have these expensive confidential models with so much with data that they spent millions of dollars for. And obviously they don't want to share it with other people. But if they have a public API, the public can query inputs to it and get an output and train their own model on it without any knowledge of the type of model, the hyperparameters, or the distribution of the training data. And so basically whenever you have a machine learning model, it's kind of susceptible to this kind of attack. And this is why the HMDs have a flaw that can be exploited. And so that flaw is the ability to create evasive malware after you reverse engineer the HMD. And so once you reverse engineer the HMD, you kind of now have your own HMD that you can look into the internals of. So it's no longer a black box. And what you can do is you can take that weight vector that's applied to the inputs, and you can kind of search through it and see what features of programs being executed have negative weights that classify them to be benign. And those specific features, once you inject them into your malware, the malware will slow, like the more and more you inject into the malware, the HMD will slowly start deciding that that is now benign instead, because you put in those features specifically that the victim is trained to know as benign. And so in the top right, you can see that for a neural network that classifies malware as either benign or malignant, once you start injecting these negative weight instructions into the program that's being executed, the accuracy of the model at detecting the malware as malignant starts to decrease significantly. And this applies to all models, not just neural networks, but also like logistic regression and all types of classifiers. And so this is obviously a terrible thing, because now you can kind of just create malware that goes around the whole model you've been training to detect the malware. And you might be saying, well, why can't you just retrain the HMD in order to now detect that evasive malware? Well, you could, but then the thing is that the evasive malware can do the same thing by reverse engineering the HMD, again, injecting weights that cause it to be classified as benign. And then you have this whole problem over and over again. And you kind of have this cycle between the HMD and the evasive malware. But in the end, as you can see, as this keeps happening over time, eventually the HMD will not be able to detect anything, whether benign, malignant, evasive, with any sort of accuracy whatsoever. So in the end, the evasive malware will always win against the HMDs. And so the threat model that this paper says is that the attacker has access to an HMD, and they even has a black box, and they can reverse engineer it to create their own evasive malware. Another assumption that the paper has is that the malware isn't completely obfuscated, such as putting one malignant instruction in like a million benign ones, because it's really hard to detect that even with any sort of detector. And in that case, the malware is just completely useless because of so much overhead, so it doesn't really accomplish much. So we assume that the malware isn't like completely useless. And another thing is that if the HMDs retrain on that malware, you can just create evasive malware, and the evasive malware will always win in the end.
All right, so Bob posed a lot of issues associated with HMDs. Let's talk about how this paper scoped and addressed them. So on a very high level, the paper just tried to build these resilient HMDs, and they targeted them as our HMDs. So once again, the high level overview is that they stochastically, we'll come back to that part later, they select different detectors that are trained on unique features. So let's take a moment to talk about what detectors and features even are. So features are kind of like the aggregated group we talked about earlier. For example, you have some features that are talking about instructions, instruction mixes, you have memory accesses, you have architectural features. So all these categories fused together form some sort of feature vector. So you have like one feature vector for instructions, one feature vector for memory. And then end, you train different detectors on these feature vectors. Then you have one detector for like instructions, you have one detector for memory. And after you have these different detectors, you have the HMD stochastically, which means it's probabilistic and not deterministic, select between these different detectors. Let's talk about what that accomplishes. Because now you can introduce some sort of uncertainty into your system. You're not entirely sure which detector you're going to choose at a given point in time. This makes it incredibly difficult to reverse engineer. So the paper backed this up later with a talk about something known as PAC learnability theory toward the end, which illustrates that if you have a system with increased variability, then it actually becomes incredibly hard to reverse engineer this system. So they achieve this sort of randomization or uncertainty in two clear ways. So the first one is pretty obvious actually. If you increase the number of feature vectors or detectors, as in you have a larger pool to draw your detectors from, then it becomes even harder to reverse engineer. For example, if I have a pool of 2 detectors versus if I have a pool of 4 detectors, then it becomes exponentially harder for the attacker to try to reverse engineer a model that's pulling from a pool of 4 detectors instead. So if you want to take a look at the diagram toward the right, you can see that as you have 2 feature vectors or 3 feature vectors, the accuracy of the system sort of drops out. So another one is that you can, this one's actually less obvious, in that you can record data at different frequencies. So what this means is that if you say sample your instruction data at 10 kilohertz, you actually want to downsample it to also sample it at 5 kilohertz. So now for that given detector, you actually have 2 sorts of data that you can choose from, 10 kilohertz and 5 kilohertz. And because your neural network is going to, or your machine learning model is going to be taking in these data as inputs, or using it to kind of classify, if you have these different sampling rates, it's actually going to change something about your system as well. So by having recorded data at different frequencies, it introduces a further level of uncertainty and makes it even harder for someone to try to reverse engineer your system. All right, so now that we've talked about the solution, let's talk about how we evaluated it and what they found. So the first step is essentially simple. Just implement various kinds of RHMPs, and then they have like 2 detectors in the same period. They have 3 detectors in the same period, 2 detectors with differing period, and 3 detectors with differing period. Next, they just simply attempted to reverse these RHMPs the best that they could. And from that reverse engineered RHMP, they tried to test them in varying amounts of the basic instructions to be able to see how they perform. So let's see how they perform. In this diagram on the right, you can see that when there's 0 injected instructions, which means that the program basically behaves as normal and there's no really malignant activity, you can see that all of the RHMPs perform quite similarly. The simplest one, 2 features, actually slightly outperform the other ones. However, as you increase the number of injected instructions, you can start to see the trend that more variable, more uncertainty RHMPs start to drastically outperform their less variable counterparts. For example, when we take a look at the extreme case, 10 injected instructions, we can see that 3 features with periods actually almost outperforms 2 features plainly, but more than 50% accuracy. So with this, talk about evaluation. Let's first talk about like the metrics that they use to evaluate them, right? So the first one is obvious. It's just classification accuracy. You're able to classify malware as malware and a normal program as a normal program. Next, they also talked about trying to implement this in some sort of online system with the FPGA. And in that, you had an area increase in the FPGA of 1.72% and a power increase of 0.78%, illustrating that while there is overhead for implementing this, it's not as significant as it could be.
Okay, so that was kind of the experimental evaluation of the solution. However, one thing I thought was really cool about this paper is that they also had like a pretty rigorous mathematical foundation as to why stochastically picking between different detectors is better. And so basically what it is at a high level, as far as I could understand, is when you have a large number of low accuracy classifiers, when the attacker tries to reverse engineer and train on that, the error from the low accuracy classifiers that you have kind of propagates into the attacker when they're trying to figure out what the decision boundary is. So it makes it like exponentially harder for the attacker to figure out what the decision boundary is. So you might be wondering, why would you want a bunch of low accuracy classifiers? Like, wouldn't that make it harder for you to detect malware in the first place? But because we're like switching between detectors and averaging the results and averaging the decisions, overall, the accuracy is actually pretty high at detecting malware and benign programs. And so one flaw is that the attacker still can reverse engineer these RHMDs, but in order to kind of figure out what that more complex decision boundary is, it takes exponentially more samples. And so it's kind of assumed in this paper that that's not really feasible. And thus these RHMDs are kind of more resilient. And I didn't have a picture for the slide. So here's a picture of my sister's cat being a menace and lying down on the kitchen counter. Okay. And so some potential future work that could build off of this paper and actually have built off of this paper that we found is creating non-stationary decision boundaries for each of the detectors in an RHMD. And the way you could do this is kind of each time a detector is running, randomize the set of features that it's training on, and that makes it harder for the attacker to figure out the decision boundary. Another thing by the same authors of the paper is they can use something called voltage overscaling, which also makes the decision boundary more stochastic and random. So that's another way of making these RHMDs a lot harder to reverse engineer. And so some other stuff that we thought would be useful is some follow-up about like, what is the optimum number of detectors to put? What is kind of the trade-off between complexity and overhead, right? Like as you have more machine learning models that you're switching between, there's kind of a lot more overhead. You just store all that information. So what we kind of want to know, like at what number of detectors is it enough to kind of say, okay, this system is unbreakable?
Right, so that brings us to points that we have for future discussion. So throughout this class, we've seen this constant theme of randomization being used to try to secure systems. In this case of RHMDs, we use this stochastically selecting different detectors. We have different computers that are also stochastically selected. But throughout this class, we also saw cryptography. We use a nonce, which is a randomized value, to be able to try to encrypt our values such that we wouldn't be able to see certain messages associated with certain ciphertexts. So I suspect that we'll be able to see that this trend of randomization be very important to try to secure systems. We also have another question of how quickly RHMDs can actually be adapted to new malware, since you kind of have to obtain all this HPC data and train new models online. So that's something to keep in mind when implementing on the actual system. Furthermore, we also have the question about if different system architectures play a role, if they record data slightly differently, how that would impact the RHMDs. And as Bhavin mentioned earlier, how exactly overhead scales as the system becomes more diverse. And finally, we just wanted to pose a question to you guys. This paper seems incredibly watertight. They have their theoretical section at the end. They have so many evaluations. So how can such a system be broken? We couldn't really figure that out, so we just wanted to pose that to you guys and have something to think about. And I think with that, presentation comes to an end. So thank you so much for listening.
All right, thank you so much, guys. Any questions, comments? Yeah, as I said, this generic term of RHMD is actually like, keep going actually even after this work. So it's kind of like, people keep coming up with, oh, there's the evasive plus malware that that can now, like, now we can figure out how you stochastically choose your malware detector, and now we can actually circumvent that and so on and so forth. And then there's another like RHMD plus, which is kind of like say, oh, okay, so I'm kind of like, you get even a better job of randomizing and so on. So yeah, unfortunately, there's no like a systematic, there is no theoretical guarantee of what we can do in order to fix this issue. There's also people who are kind of like, very skeptical of general hardware malware detectors because usually the problem is that as you're collecting these features that we mentioned, right, from the performance counters, there's also lots of other processes also going on that is not necessarily relevant to the process that you are trying to monitor. And as a result, there's lots of junks and noise that's coming and kind of like compromising or polluting your samples. And this can create lots of false positives because then your malicious code can also look very similar to those additional unit notices. So it's an interesting area of research, definitely, but there are lots of challenges as well. But thank you, very good presentation. Okay. Stop sharing. Start the lecture. You guys have midterms coming up?
Yes.
That's the point. There's not that many people here today. You guys are well, probably. Okay. I'm still wrapping my head around the quarter system on it. It's like we just started and now we're
Yeah.
week 5. It's almost half of the class.
On campus.
Alright.
Really nice little apartment. Subsidized.
Okay. Just checking that we're recording. Yes. Voice is there. Alright. So today I want to talk about memory safety. So we did the paper presentation. So now let's actually go and dive into what is memory safety. So remember, when we were talking about malware detection and how malware works, I told you that essentially the attacker has multiple different options.
Yeah. Are you presenting slides?
Oh, sorry about that. Good. Okay. So we talked about basically different options that the attacker has. Obviously, the attacker can just into the system, go into the system to steal something from the system, right? Some private data, password, etc., etc. So that's option number 1, which is very popular option in many scenarios. The second option is the attacker wants to do something harmful and change something, right? So that could be either some values in the system or some even codes in the system, and the resulting impact would be something like ransomware or something like various type of viruses that be sensitive to this, right? So kind of like executing the payload that he wants or she wants by changing something into your program. It basically breaks something, right? And finally, the third one, which is kind of the most popular one, is the attacker wants to take control of the system in order to be able to run something else, right? And most of these malware types that we discussed eventually wants to do this because he eventually wants to take control and start executing something malicious. Remember, we said that usually this involves downloading something and then being able to run that, right? So you need to kind of like first inject the code and then finding a way to run those things, right? And if you remember in the malware detection, I said that for now we're just assuming that we find a way of penetrating into the system and injecting our code, and now we're talking about the impact. So now we want to talk about the first phase, that how do we actually penetrate into the system, how do we actually load our code into the system, and so on. And the gateway to that is basically the memory, because essentially the way that we execute things, before I go to the next slide, the way that we execute things is we have our core or our CPU, and we have our memory here. And most modern computers are usually using this memory core system, basically, which essentially instructions are stored here in the memory. The core is basically just is this instruction execution machine which go grab one instructions, execute it, go grab the next instruction, execute it, and so on and so forth. So instructions are kind of stored in the memory, right? And the code goes and run this instruction one by one and move forward, right? So in order to being able to take control of this system and start executing something malicious, what the attacker wants to do is basically, just execute something different. So load something into the memory and force the code to actually execute that one. So you normally run these things here, but now if the attacker managed the victim to run and start executing code to run this part, then it can actually take control of the system. And that's what we're going to discuss in more details in the next lesson. All right. Just generally the idea of how we are attacking the system and how we are forcing the system to start executing on. Okay. So to understand how this works, I mean, I already gave you a little bit of background of the memory structure. I told you that basically what we have is that we, instead of dealing with the actual physical memory, we tend to use what's called a virtual memory, which essentially every process in our system thinks that it has access to the entire memory. The memory from the program perspective is unified and is completely private. So basically what each program thinks that it has is basically the entire size of the memory, which is unified. So the addresses can start from 0 all the way to whatever the size of the memory is. So for example, let's say we do 32-bit addressing. If that's the case, the addresses in our program is any number between 0 to the power of 32 minus 1, right? And this is the same story for program B, also thinks that it has access to the entire memory and so on. And we talked about how we actually translate these addresses to the actual physical memory addresses, because physical memory addresses is actually where we store all these things, right? So we had this page table somewhere here, we did the address translation and so on and so forth. If you don't remember, I recommend you to go back and watch the past two lectures when we talked about how to read the address terms. All right. So this is the story so far. We have virtual addresses and physical addresses. Usually within each process, we tend to use regions. So the regions kind of like, we divide the memory into pieces and try to kind of categorize and organize things. So we usually have some reserved part. We define some region called code region. We have a data region, and typically we have what's called heap and stack. So the code region is really where you store your instructions. So if you program a many line of code, that's been compiled into binary code, and that's where you store your instructions. So this is basically a bunch of zeros and ones, which translates into the instructions: add, multiply, stop, memory, load, store, etc. Okay. Then you have your data part, which essentially are all the initialization values that you want to work with in your program. That's where you store all of those things. And then you have the dynamic. So this is mainly the static part of your memory. And this part here is the dynamic part of the memory. So the heap is where you store your dynamic variables, right? So if you have an array that you dynamically change the size, that's where you store it into a heap. And as you can see, heap is kind of something that can grow. So it's not like a fixed size. It grows in one direction. So for example, in this example, it grows into higher address directions. And then you have something similar to heap called stack, which basically where you store your temporary or local variables. So for example, when you call a function, when you jump from one function to another function, you want to store something temporarily, stack is where you store all these things. We're actually going to talk a lot about stack because that's the main issue in the processors and the way that we actually can attack this. And usually a stack grows into opposite direction of the heap. So we usually have this free space here, which heap and stack kind of like grow into opposite directions and competing for that. Usually this free space is big enough that both of them can comfortably grow, but there could be at some point that's this part is filled, So you no longer can put more things into your stack.
Isn't this figure like upside down because stack grows down and grows up?
What do you mean by upside down?
So I mean, in address space, stack grows down. Equals.
So that's so whether a stack grows up or down, really it's microarchitecture dependent. So it's not something that's always, your stack grows down or grows up. Just as I said, this is an example. There is nothing that just tells you that always your stack has to grow up or grow.
Just going off that question, I forgot to say clearly how it goes, but does stacking start at the opposite ends and then converge together as they grow, or do they start at the same point and diverge as they grow?
So usually in order to make things slightly easier to manage, they're on the opposite direction,
Okay,
but
converge,
they converge, yeah. But it's not something that's necessarily, you can design your memory system such that they grow in opposite in the same direction.
Oh,
So that's like slightly more difficult to manage because then you need to manage your free space a little bit better. But that's usually operating system dependent and microarchitecture. So like ARM is different from AMD, from Intel, and so on. And so on. Okay. But generally, what you need to understand is you have some sort of like a fixed block in your system. It's actually there's more than coded data. I just simplified the image for you. And then there is kind of like dynamic part that's kind of grows. So in one direction or another, that doesn't matter that much. Okay. And then every program has their own address space and their own structure of growing up or down and so on. Okay. So how do we execute a program? So think about, for example, we want to execute program A. What would happen is that when we want to run this, usually the operating system loads this into our memory. So kind of like, we load this into our main memory. So this obviously would be a very small portion of our main memory. And so we load this into our main memory. So as I said, we have a CPU core here, and we have our memory here. So this thing here actually goes into our main memory. Let's say this would be compact and this would be here, right? So what happened next is, so generally the way that we are running things is using this very special register, important register called program counter or PC, okay? So what does the PC do is that if you look inside the CPU, you have a machine that's basically run instructions. And it has this register, which is kind of like think about it as the index or the pointer to the memory. Then it goes into that line of the memory and bring that one instructions. This instruction goes into the PC. The PC will execute this. Then usually increments the PC by 1 or sometimes by 4. That depends on the structure. But think about it as next instructions. So going to here and runs the next instruction. So let me show you the color. So PC plus 1. So PC plus 1 would be this next instruction here. And the story continues. So then you go to PC plus 2. PC plus 2, and so on and so forth. So we kind of think about this as a register that goes one by one instructions to run things. So PC plus 1 goes into the second content of the memory, then the next one, next one, next one, next one. All right.
So this is different from like for example, if you look in simple code, there are like line numbers, or this is like the same concept. Right?
Say it again.
This is different from like the line numbers or instruction numbers and stuff, right?
So the line numbers may or may not be exactly the instructions. So some instructions might be multiple bytes, some instructions might be 1 byte. But think about it as basically your instruction is one instruction is what the granularity that you want to execute.
So like if there's a loop somewhere in assembly that the instruction numbers may repeat, but the program counter
the program counter also repeats, right? So for example, let's say you have a loop, right? The loop is basically a bunch of instructions. And at this point, you have to go back to here, right? So your program counter will be pointing here, then pointing here, then pointing here, then pointing here. And at this point, you have to change and go back to again pointing here. Okay. So you keep repeating this until your loop condition is not met anymore, and then you continue moving forward. Okay. This makes sense? Okay. So again, so what happens is you have a program counter. It's kind of like keep track of what you're executing right now. And basically you execute one instruction and you go to the next instruction and you go to the next instruction. So going back to the example that I was showing here, where essentially we wanted to have a CPU and a memory. So our CPU is here. And let's say this is our PC, it's one register. And our memory is here. And let's say the program that we want to execute has this portion of the memory, right? And then basically think about it as multiple lines here, right? So the way that we start executing program is the operating system will tell the PC to point to the beginning of this part. So at the beginning of this program, that's where the PC needs to point to at the beginning, right? And then afterwards, it basically just keep incrementing by one until we reach to the end. That's where the operating system again takes over, runs to the next instruction. It's next program, right? So basically, the life cycle of an instruction is the OS loads the program into memory, then OS initialize PC with the address that points to beginning of, okay, and then after that, PC increments until the, okay. And this story continues for every single program that you use. Okay, like clear? Any questions here? And usually this CPU memory model is what's called a von Neumann model. All right. So von Neumann is when we are putting things into our memory and have a PC that's kind of like pointing to that and reading these things. Okay. And an alternative to this is other type of architectures such as data-only architectures, where you essentially don't run the instructions, but you run the data flow graph of your system. So usually like accelerators or something like that, but that's a separate story for a different course. For now, just remember that's how we execute. Okay. So now the question is that given that this is the format that we are executing things, how we can hijack this, and we usually call this hijacking the control flow. This is the control flow, which means that the flow of your program is like this. You're controlling the flow because you're starting from first instruction in the program, the next instruction, the next instruction, right? So now the big question is, how do we hijack the control flow? And the idea is very simple, actually. So again, going back to the core, if this is my CPU and this is my memory, and this is kind of like the part that I'm executing things here. So and these are the lines. What the attacker can do is that if the attacker, let's say with one, for some reason the attacker managed to inject the malicious code here. So the malicious code is basically staying in the memory somewhere else, not in the part of the program being executed, but somewhere else in the memory. For now, just imagine that the attacker managed to find a way to inject that. What the attacker can do is that if the attacker can force this control flow, this PC plus 1, to instead of like maybe in the next time executing this instruction, jump to here and start executing this instruction, then basically can take control of the system and start executing this malicious code, right? Because from the CPU standpoint, CPU does not know what is executing, right? The only thing that it understands is that this is the value of the PC that I have, and next time I'm going to just increment PC by 1 and go and execute the next instruction. So if you kind of can force this PC to, instead of pointing to PC plus 1, maybe pointing to PC plus some offset, and that offset is the beginning of this program, then we basically what we call hijacking the control flow. So now we can actually, instead of executing this legit instructions, start this malicious instruction, right? That's what we call hijacking the control flow. We're disrupting the way that PC is operating. We kind of force the PC to get a value that it has no idea that it's not legitimate. And this way, we actually forcing the system to start executing those malicious instructions instead of normal instructions. Does that make sense? Anybody have any questions? Cool. So let's see actually how do we do that, because that's not a simple task. So two main questions, right? So how do we inject this malicious code here? And how do we force the PC to jump into that section of the program? Right? So these are the main two questions. And this is basically what is generally known as memory safety problem, because essentially your safety is this assumption that your program should be able to just stay within the same program, basically, right? So it should stay and execute those instructions that you're expecting. If the memory is kind of compromised, and then part of it is actually compromised with malicious instructions, then PC has unfortunately no way of detecting that, and will start injecting and executing something that is not legitimate, right? And this is like one of the very, very old problems in computer security. Actually, it's one of the first ways of attacking systems. And given that there has been lots of time and effort on this, unfortunately, this is kind of like there's many sophisticated attacks in this, and there is not much things that we can do. There is lots of ongoing war between the attackers and the defenders in this, which we can actually talk a little bit about. And usually the reason for these potential memory safety problems is software bugs. So the way that we implement the software, we don't do certain checks that we needed to do. And because of that, the program is vulnerable to these attacks. Once I describe it, we will understand how this actually works. And then later on, we're going to talk about the defenses and the challenges with the defenses. All right. So now let's talk about buffer overflow. I'm sure most of you already know what buffer overflow is, but let's actually go a little bit more details about buffer overflow. All right. So again, to show you how the memory layout works, this is like a slightly more complete image of the memory layout. So the text is basically the same thing as I showed before. Code, data, you have the other areas that you don't need to be worried about that much. But again, you have your heap and your stack, which is kind of like throwing into opposite directions, right? Or as I said here, it could be stack here and your heap here. That could be the direction that you're here. So to understand how buffer overflow works, you need to first understand how the calling convention works. Basically, calling convention is what is a set of certain rules. When we call a function, we need to follow those rules, right? And typically, that's what the compiler does and what the hardware needs to follow when it does it. Okay. And the reason we need calling convention is because we want to write our programs in a modular fashion. So we want to run things in different functions. We can always run it in one same function, but that's not what we do in advanced software engineering systems or in advanced software. We usually have multiple objects, functions and so on and so forth. And as a result, we need to be able to, you know, call different functions and return back and call another function and return back. And so on. So it's kind of like in a game between convenience and then adding more complex features, but being able to, you know, accommodate for those complex features. Well, let's actually go through the calling convention and see how it works. So it's kind of like three major rules for calling. When you're calling a function, so obviously there are two parts in calling a function. There is a caller and there is a callee. So let's say you have, for example, your main function, and you do some stuff in your main function, and at some point you call a function, let's say call it foo. So main is the caller and foo is the callee. And so what will happen is so the first rule is what is the callee needs to, like, you know, make sure. So when we are jumping to the foo, so usually we have a bunch of different registers that you can play with. So for example, in Intel, you have kind of like 16 different registers that you can play with and change numbers, right? Some of these registers are actually what's called reserve registers. And the way it works is that, for example, when I'm calling a function from main to foo, obviously I have some local variables here, right? And these variables are maybe stored in some registers, right? And when I'm calling the function foo, the assumption is that whatever function foo does, and when we are returning and start executing the next instructions, the assumption is that we still have those values into one register, right? So whatever foo does, they have to make sure that they don't mess up with those register values, those stored values, right? So usually there is a standard that, you know, these registers are callee registers and these registers are caller registers. Basically what it does is that, think about it, that if you have 16 registers, for example, 8 of them are reserved for the caller, which means that if foo wants to really use, so first of all, the foo has to avoid using them. But if foo really wants to use them, they have to kind of, like, you know, back up the previous value somewhere, use those registers and recover those values, okay? So that's usually what it does. For example, let's say there's register number 8, and this register is a reserve register. So if foo wants to write something to register number 8, what it does is basically first say register number 8. And the way that it does this is basically pushing these things to the stack. So this would be our reg 8. And then start messing with reg 8. And then when we want to return back to the original function main, just right before returning back, we need to recover this register 8 back to the register 8. So we're going to pop this stack into register 8. Okay? And here I'm not using a specific syntax, so just I'm using a made up syntax. So for example, Intel would be EAX or EPX and so on and so forth. And things like RISC-V would be R1, R2, R3, and so on. But just think about it as number of registers. Okay? So this would be our stack. If we want to use a register, we need to first save it and then mess up with it and then recover it at the end. Okay, this is one of the main rules for the calling convention, and only for the reserved registers, not for all the registers. Some of the registers are generally designed for the callee, and the callee can just, you know, start, you know, changing them without being worried that what will happen, because the assumption is that main is not going to use them. Okay. Any questions about this part? Is it clear? Okay. The second thing that, you know, for the calling convention we need to be careful is that when we are calling a function, so we are in, so this is our stack, and we are, you know, saving a bunch of stuff in stack for main. So we usually call it frame. For each function, we have kind of, like, you know, a collection of things that we want to store, and we call that a frame. Okay. So So this is, for example, a frame for the main. And then at this point, we are having a main function here. We have a bunch of instructions, and now we are calling foo. Okay. So at this point, what we need to do in order to jump into foo is that obviously this is the value for PC, right? So this is value x, and this value x is pointing to the calling this function. And here PC would be x plus 1, right? So it's its next instruction after calling foo is part of the main function, right? So what we need to do is that when we are jumping to the foo function, we need to always be able to return back to the main, right? So whenever you call a function, your function ends with a return instructions, where you need to go back to where you were, right? How do we know that where we are going back? So basically, in order to know that, when we are calling foo, the first thing that we do is that we are storing the return address here. Basically, what we are storing here is PC value that is equal to x plus 1. So we basically store x plus 1 into this point, right? And we push this into the stack. And then when the foo is actually being executed, so let's say we have a foo function here that has a bunch of different instructions, and at the end is actually the return function. So when we are reaching to this instruction, what it does is basically going to the top of the stack, which at that point would be here, and it's gonna just jump into this address, which is x plus 1. Okay, so it's gonna jump into this address, which means that we're gonna jump into this point, which is exactly the next instruction after, and then we can continue, running the instruction, right? So when we're calling a function, we need to kind of remember where we're gonna go back. And in order to remember that, we're gonna store this address into our stack. We're gonna put it into our stack, and when we are reaching to this return instruction is basically just update your PC with this value. Just whatever we are storing here, the PC would be that value, and the next instruction is going to be executed would be that value. Okay.
Are registers stored on the stack? No,
The returns.
the registers.
So the registers themselves are registers. Think about it as reserved memory.
Yeah.
But if you want to change the value of register and that register is reserved, you need to store that value into your into your stack, then start changing that, and then recover that value. So basically, your stack is kind of the backup for your registers. Okay, so it works as the backup. If you want to use more registers, you can always back up the old value into the stack, changing the things in the register, and then recover that value once you're done. But for the return specifically, there is no specific register for the return. What we usually do is that we push the value of the return address into the stack. So the stack is where we store the return address, and that's very, very important for the buffer. Clear? Any questions here? Okay. So this return part is very, very important. And then if we keep, calling function after function after functions, whenever we're calling a function, we need to make sure that the return address actually goes into our stack. Okay. And the final thing is, before returning, we have to also recover the frame pointer. All right. So the frame pointer, as I said, for each function that we are calling, so if I put the stack one more time, let's say we have a bunch of different functions. So this is our stack, and these are a bunch of different things that we store. And this is just generally for the main function. At this point, we call it foo, and maybe inside foo, we're calling another function called var, and so on and so forth. Multiple, inner functions together. And generally, since each of these functions needs to store some local variables into our stack, we usually call this, all the relevant things into stack a frame. So this is the one frame, this is another frame, and so on and so on. All right. And in order to make things easier when we are jumping from one function to another function, and when we are returning, there is this specific register called the frame pointer. let's call it FP, the frame pointer, which is kind of like, pointing to the beginning of that. You usually call it, BFP or like base frame pointer. Which is basically saying that, okay, this is the beginning of your frame for main function. And then when we're jumping to the foo, we're gonna update this with this value that's pointing to here. When we are jumping to bar, we're gonna update it to this value. And now when we are returning from bar to foo, we can just, just update it back to this point. So to just know where the relevant information about that specific function is stored in the stack, we usually have what's called a base frame pointer to just show you the beginning of that. And everything else would be an offset to that, okay? So if you have, like, let's say 4 different local variables in this foo function, in order to, for example, extract this 4th one, all we need to do is that adding this BFP with number 4, for example, okay? And this way we can very easily find all the local variables for all the functions. So one of the main part of the calling, the returning is that before we return, we need to also update the frame pointer back to where it was. So when we are starting from main, it was here. Then we call foo, and then we update it to here. Now, when we are done with foo, we need to update the frame pointer back to the beginning. Right? That's one more thing that we need to do. And as a result, the same as saving the return address, we also save the old frame pointer so that we know that where we need to point to once we return. Okay. Any questions from the calling convention? There are also another minor things that I skipped, but just these are general 3 things that we need to. Okay. So another thing to understand before we actually jump into how buffer overflow works. I already discussed this, but one more time to make sure that everybody know what these are. You have what's called the control flow instruction. So the control flow instruction is basically what impacts the PC. So remember I said that PC start with some initialization value that points to the beginning of the program. And basically what you do is that PC plus 1, PC plus 2, and so on and so forth. There are certain instructions that generally change the value of PC as needed. And 4 main ones are the call, return, direct jumps, and indirect jumps. So think about like things like if and else functions, right? So if you have if and then some instructions and then else some instructions, if your PC is pointing to this point of your program, the beginning of the if the condition is true, the PC should be PC plus 1 and start executing this instructions. If the condition is not true, your PC has to jump from these blocks and start executing this blocks, right? So it's not no longer PC plus 1, it has to be PC plus some offset in order to jump over that if condition, right? And in order to do that, we need this jumps function or indirect jump function. The difference between jump function and indirect jump function is that jump function usually jump the PC to a specific value. So it's just saying that PC plus some specific offset or whatever you want to call it. And this offset is already known. So we already know that, add PC with this value or minus PC with this value if we want to jump back, okay? If we want to do the indirect jump, usually what we do is we're saying that PC gets the value of some register, right? So whatever the value of that register is, jump to that value. And usually call it indirect because it has to first read that value of the register and then go jump into that address, okay?
Sorry, this is going a couple of slides back, but what's the difference between the frame pointer and the stack pointer?
Stack pointer just show you where's the current where is the top of the stack is right now. Frame pointer points to the beginning of this frame. So if you have multiple functions called one after another, you usually have some local variables for any of them, right?
Also, like you're talking about function within a function call?
Yes.
Okay, so like if you're within the nested function call, then like that, I guess that layer. So the frame pointer points to the top of that layer of function call. Like you're calling F2, then F1, and then F3, then F2. Then
Yeah. So again, you have to understand what is frame. So frame is just basically whatever is relevant to that function. And when we are jumping to another function, we create a new frame.
Okay,
Which
so
is
like
basically
frame points to the top of frame,
each frame, exactly,
aka like each function with their frame.
kind of, yes.
Right.
You have one frame pointer or multiple frame?
One
pointers?
frame pointer, right? So you always point to the beginning of this, so you're always in one function generally, right? You can
Oh.
never be into two functions. So all you need to know is where is the beginning of this frame, and you always have the backup information of where is all the old frames. So when you're done with this function, you need to go back to the beginning of the previous frame. So you save that number in your stack. When you want to return, you just update that frame as if nothing happened. So you jump up or down depending on which direction your stack is going. And this way, it's like you're back into your original function, whatever it is.
Thank
Right? And then you can just infinitely jump this basically, right? Because you can infinitely return to the previous one and the previous one without being worried about this. Okay. So yeah. So we need, and then call and return are basically same as jump functions, but just a specific type of jump functions, right? So it's just jumping to the beginning of the function or to the end of the function, right? So that's the only difference between jump and call and return. Call and return is nothing specific, it's just type of a jump, indirect return jump. Okay? So, I mean, we really need jump functions and indirect jump functions because otherwise we cannot do control flow. We cannot do if and else, we cannot do function calls, we cannot do loops, we cannot do whiles, we cannot do any of those without these jumps, right? Because if you just, just linearly add your PC plus one, PC plus one, you never can have if then else, you can never have while loops and so on, okay? So this is like vital for the correct execution of your function, but as you will see, this also causes lots of headaches and lots of challenges. Okay, so this is kind of like just a quick recall of what we just said. So calling convention and the stack. So here's how it's going to work when we are calling something into our stack. Okay. So here's our stack. And let's say that we are having some chunks that is relevant to our main function. And this is our EBP, which this is the terminology for Intel processors. So this is the register that points to the beginning of the frame for the main function. All right. So this is the frame for the main function. Okay. So what happens is that the main function wants to call foo. So you have your main function here, bunch of instructions, calling foo, and then bunch of other instructions. All right. So your PC now pointing to this instructions, and now you need to call foo. All right. So what will happen? On the caller side, on the main side, two things we need to do. First, sometimes obviously we want to pass some arguments to the foo functions. The way that we pass those arguments into the foo function is basically the caller will put those parameters. We'll put those parameters in here into the just write down the stack. So this would be like input number 1, input number 2. And so on and so forth. Let's say it has multiple inputs. Okay. So if you're calling a giant function with many inputs, you usually put all of those parameters into your stack. Okay. So the first thing that it does, then it basically call the callee by changing the PC to the beginning of this foo function. So this foo function is stored somewhere into the memory. So we need to, at this point, we need to change PC to, PC has to get the beginning of that function. Okay, so that was what we do. And then another thing that we do is we're gonna store the return address here. So the return address also gonna be stored here. Okay. And this is basically becomes the kind of like the beginning of the new frame. Okay. So what we need to do is now we need to store the frame pointer here as well. The old frame pointer, this one. Let's call it old. So all EVP gonna be stored here. And if there is any sort of registers that we want to change, one of those saved registers, we also need to just put them all in here as well. Okay, and these are all the saved point registers that we're gonna want to change in the future. Okay. Then what we do is usually gonna extend this stack to save our own local parameters. So this would be our own local parameters. Local parameters means parameters that's gonna be used in your foo functions and not in your main function. And that would be it for this calling convention. Once we are done, we need to kind of reverse these steps in order to restore all the values that we have and jump into the function then. Okay, so this kind of like, where it happens to a stack whenever we are calling something. Then we start executing the instructions. And when we are done, we need to kind of restore all these steps one by one. So we need to restore these register values. We need to restore the base pointer to here. And then we need to return this function. So after a while, we need to, PC should get the value of, let's call it X, should restore the value of X plus 1, and then jumps back, which means that now we start executing this. Okay? Does it make sense? Cool. So this would be how our stack would look like, right? When we're calling a function. And this is basically just a regular and conventional way of calling a function and using our stack function. Okay. So now the question is that, is there a way that the attacker can actually misuse this? And remember, the goal for the attacker was either modifying some values, right? Or we want to hijacking the control flow, right? We want to be able to, instead of, for example, jumping back to PC X plus 1, maybe jumping to X plus some offset, and this offset is somewhere else in the memory. So if you're, let's say this is our main, this is our foo, so this is our main. This is our foo. And let's say somewhere else down here, this is our malicious code. So if we are in foo and we are reaching to the end of the foo and we want to jump to X plus 1, instead of jumping to X plus 1, which is kind of like somewhere in here, maybe we want to force the system to jump to X plus something else that is beginning of our malicious code. And this way we can actually attack the system, right? So let's see how we can do that. Before that, let's have a 3 minutes break and then we can come back. This is okay. So yeah, just a reminder, this is how our stack look like. These are the local parameters for your main function, right? Then these are the inputs that you want to pass to your foo function. This is the return address, which is in this case is X plus 1. This is where once we are done with foo, we want to go back. We want to load our PC with this value. This is the pointer to the beginning of the frame pointer of our previous function, which in this case is the main function. So basically this EBP is pointing to this address. Then, as I said, if we want to store some of the things that we want to change later, we usually store them in here. And then these will be all our local variables. And in this case, our EBP will be pointing to here. This is the beginning of this frame, right? So all these things are just kind of like, utility information that we're going to use later. But all our local variables that we're going to use in foo function is going to be somewhere here and downwards, right? So that's why the EBP is pointing to this point there, okay? And your stack pointer, which we usually call it ESP, is always pointing to the top of your stack. So that's why you have an EBP, which is kind of like pointing to the base, to the beginning of your frame, and your ESP or stack pointer always pointing to the top of your stack, because there are lots of push and pops that you want to do, which has nothing to do with where your base is. Okay, so that's the story of returning. And then, as I said, when you're returning, you kind of like go into this direction, right? So you kind of discard all these. You have to restore all these things first. Then you have to restore your base pointer. Then you return, and you're done, right? So you go back to this point, and everything is as if nothing ever happens, and you never even called foo, right? So you can just continue with your normal life as before. Okay. So now let's see how we can actually exploit this, and what is this fuss about a buffer overflow. So the buffer overflow is actually a very interesting thing to do, and what happens is if you're kind of like have some sort of a buffer, where you, for example, in your foo function, you have a bunch of instructions, and at some point you do something like getS or getLine or something like that, depending on which syntax we're talking about. Which this getS is basically waiting for the user, waiting for the terminal, waiting for whatever the I/O interaction is, to send some sort of inputs to the system. Could be integer inputs, could be string inputs in this case, anything, right? And the assumption is when we are compiling this code, we're assuming a certain size for our input, right? So we basically, depending on where we're going to store this, we, for example, assume that this is going to be 20 bits. The 20 bits is just a random number I just put in, okay? And this value that's going to get here, we call it buffer. And it's going to assume that we're going to get 20 bits for this buffer, okay? So what will happen if we don't send 20 bits and actually more than that? That's where the kind of the magic of the buffer overflow actually comes into play. And what happens is that you're going to store everything, not only that 20 bits here, that's the regular 20 bits that we can do. And now let's say instead of 20, we are storing 30 bits. And what will happen is that since that value is not going to fit into that 20 bits, they're going to be 10 extra bits spillover. We're going to start overwriting things into the upper direction. And so what would happen is that all those things that we said that's going to be stored into our stack. So if you start overwriting things, basically what we're going to overwrite is that we're going to overwrite here, we're going to overwrite here, and depends on how long we are storing things, we can go all the way to many higher places. We're going to overwrite everything that we can have just by sending much larger value with our input, right? And that can be a huge problem, right? Why? Because think about what we can do with this overwrite. Major things that we can overwrite is the return function, and we're going to actually describe how this overwriting the return function can create lots of things. So very basic thing that we can do, just forget about the return function. What we can do is basically by overwriting these things, we are basically satisfying that requirement that I said before, that we want to modify some data. Remember, these are parameters for the functions here. these are all the parameters for the functions, right? For overwriting the stacks, we are basically changing these parameters to some other parameters. So we are creating definitely we are creating some damage to the system. And that itself is an important fact and something that we need to be worried. But the story actually go well beyond this, and we can do even more powerful things with this capability. And what we can do is that since we can overwrite this function, we can actually overwrite this return address here. And what we can do is that since we know exactly what we are overwriting, what we can do is that instead of just randomly filling the stack with garbage, we can be smart and replace this with return address of our malicious code. Remember, like way ahead, I told you guys that our memory could be part for main, part for foo, and then we're gonna have our malicious code here, right? So, and then we said that essentially what happens is that once we're done with foo, we're gonna jump back into the main. So if you actually overwrite the return function and overwrite it in such a way that exactly at this part of the memory, instead of like having this return address, we overwrite it with whatever this value is. We are basically forcing the system that whenever it executes the return address, instead of jumping back into our main memory, into our main function, it's jumping into this beginning of this function, right? So that's the cleverness of how the buffer overflow works. That essentially we are changing this return address to that points instead of the legitimate place, which is x plus 1 in that example, to the beginning of our malicious code that we stored somewhere into the memory. And one thing to keep in mind is that when we are executing this instruction, we have no idea that we have done this, right? So whenever we reach to the return function in our foo, we're just gonna go and grab this value, whatever it is. We have no idea what this value was, how it got here, and so on. And that's why when we are kind of replacing this with malicious, when we are executing this return function, we are jumping to that malicious function. Questions?
Yeah, so couldn't we sort of invalidate any possibility of buffer overflow if we designed a system that makes the heap grow downward and the stack upwards? Because then if you overflow, it just goes up into space, space that's technically free and not containing other data.
So you cannot go, so the way that this works is that you need to first save some space for your local variables. And then, so the way that this works is that this is your stack, you're at this point, and now you see that you need to store another 20 bits. So what you do is you just add another 20 bits and point to here, and then store your value. It doesn't matter which direction it is. So maybe your stack grows in that direction. So what happens is, if your stack grows into that direction, your stack is here. You want to store another 20 bits, you grow your stack, your pointer will be here, and then you start storing things here. What will happen is that if this is bigger than what you're supposed to, you go in this direction always. And you start overwriting things like this. And then if you're in this direction, you're gonna start overwriting things like this. So you always, because the problem is being fit into that reserve space. If that reserve space is smaller than what you're writing, then you will always overwrite something that's an old value.
Why does the direction of writing have to be opposite the direction of the stack grows? Like if the stack grows from low addresses to high addresses, and we write from low addresses to high addresses, then the return address will always be before the start of the buffer rather than after the end. Wouldn't that just like what he was saying? Would that just completely prevent a stack or a buffer overflow because you just write into higher addresses, which would just be free space?
So the assumption here is the way that your base pointer, your stack pointer works is that you first increment or decrement your pointer,
Right.
and then you start writing things. yes, you could have done it on the opposite way, that you start writing things, but the assumption here is that you need to, so the way that the normal program works is that you always assume that the size that you're gonna write is the size, because in the, so this actually happens statically, it's not dynamically. So you're assuming that you want to get 20 bits or whatever. And the compiler only just do this increments to put more things. Remember, yes, you can do that, but there will be another value later down, like another local parameters, next one and next one, that's actually gonna be part of your stack as well. It's not like this is the last value of your stack, and after that would be free space. So for example, let's say you have getS, right? And then you have another thing such as, maybe another getS or maybe another function that reads from inputs, right?
Right.
So your stack would be here. Then you're gonna say, okay, this would be for the first getS, this would be for the second getS. So even if you're doing this work, this downwards,
Right.
still needs to reserve some space for your next local variables. And it's not like, your bottom of your stack is always free. Yes, if it was the last variables you want to store, that would be the end of the stack and everything else would be free. But generally everything, you have to kind of like put some space for each of them and then go to the next one and go to the next.
Right, but in your second example, like where we assume that the stack grows upwards, right? Why did you have to set the direction that the buffer writes to be downwards? Right? If the direction that the buffer writes is upwards, then it doesn't overwrite the return address.
Sure, but again, so I mean, the stack doesn't know that it's gonna. I see your point, but I mean, just generally the way that in order to make this work for your stack, to understand how much space it needs, you always need to reserve some space and then write things in that direction. If you write it in the other direction, then your address is like, where is your first bit and where is your second bit and where is the third bit is not known to the stack. Because remember, we want this to work in a normal way as well. That you have maybe, let's say you're writing 20 bytes, right? So you want to be A0, A1, A2, and A3, and so on, all the way. Right? You want to access all these things. And if you don't know where your end is, where your base is, then how you're gonna address this properly? That's why you always need to know that this is your base, this is your reserve space. You can only write in this part.
Right, well, we can still do that, like, if you had, say, a stack that grew upwards and a direction of writing that was also upwards, right? Because you could reserve, you could set your base at, whatever it was, and then put a return address, and then you could reserve a buffer and have the top of your stack be, the fixed offset from the buffer there, like we currently do with like how the programs normally operate. But then the buffer just writes towards the top of its frame, I guess, rather than towards the bottom of its frame, right? Then they can't write over the return address.
Yeah, maybe. Yeah, I'll need to probably plot it better for you to understand. But give me give me time. I'll post it on campus for your class. But it's not unfortunately possible. That's what I'm saying. Any other questions? You had a question?
No.
Good. Okay. But for now, let's assume that we are forced to do it this way. I'll clear that up. Maybe I'll put some images that would be easier to understand. But yeah, since we are basically overwriting something, we can overwrite our return address, and that can create lots of problems. Okay. So now the question is, so a bunch of questions. So first, we kind of found a way of overwriting the return address, right? And then we said that address could be the beginning of our malicious code. But what would be that malicious code and what we can do with that malicious code, right? So generally, when we are jumping to a malicious code, we usually call it shellcode. The reason that we call it shellcode is First of all, any malicious code at that point will do, right? So anything that does some harm, as we extensively talked about, what are those different options, ransomware, doors, viruses, different malwares, etc. All of those are the options for doing something malicious to the system. But usually, traditionally, the reason that this is called shellcode is this is a piece of code that usually invokes a shell. Shell is basically this, literally the shell, the terminal that you can start. It's a piece of program that you can run any binary code that you want, right? And when you're actually running the shell, then you have opportunity to run anything within the shell itself. So basically, all you need to do is that pointing the binary code to the shell code, and then the shell code will execute that binary for you. So basically, all you need to do is invoking the shell. Once you invoke the shell, then you have full control of running any other binary that you want in that system. You can even send something from outside, you can connect to, so you can SSH to another computer and then copy things from the other computer and so on and so forth, right? So once you be able to run the shell, you kind of virtually be able to do anything that you want with your system. And that's why it's traditionally called shellcode, but necessarily you don't need to invoke a shell. You can just run any sort of, malicious code that you want and execute that, okay? Usually we call it shellcode, but that shellcode could be not necessarily the shellcode itself, okay? There's some details of how do we actually invoke a shell. This is basically just calling a specific system call. I'm not gonna go through it, but just basically something to, if you are interested to know how to write a specific code, a malicious code that actually invokes a shell, you can just Google it and quickly find it, okay? So this is kind of like where this attacks or stack smashing attacks, in other words, buffer overflow attack works. So we need to first find a vulnerability. So it's not something that's always there. So remember, what we need is some sort of buffer or some sort of local variable that doesn't check how much information are we writing to it. So that if we add additional malicious things here, we don't check it. So the simple fix for that would have been that for everything that we write, we always check how many bits that we are writing and know that beforehand that that's the many bytes that we are assuming that we are writing. If we do that check, essentially buffer overflow is gone. But unfortunately, there are lots of complexity when we're designing the software that we could usually forget to do that check, or there are some functions that generally are unsafe to use, and some people do use it. And there are many different reasons that buffer flow happens, but just imagine and assume that there is a vulnerability like this. There is a potential scenario where there is some local variables that doesn't check how much bits you are writing, and you are overwriting that, so it's actually overwriting the rest of your buffers. Okay. The second part is you need to kind of like find a hook or find somewhere to jump to. This is basically you need to write your own shellcode. And once you write your shellcode, you need to store your shellcode somewhere into the memory. We will talk about how do you store that. Then you need to kind of, do the buffer overflow and find that address and design your buffer overflow attack such that the beginning of this code is actually where you put your return address, right? And then you start executing the code. Then it jumps into this program. Now you invoke your shell. Now you see that you have control over shell, and now you can start your original attack, whatever it is. You can run any sort of malicious activity that you want. Okay. Any questions about this? Okay. So now the question is that where do we store the shell code? How do we inject the shell code, right? And one of the interesting ways of doing this is that you don't necessarily need to inject your code beforehand somewhere else into your memory. What you can do is injecting your malicious code with the buffer overflow as well, right? So the idea would be something like this, that remember this was your original stack. So when you're doing the buffer overflow, you're basically overwriting all these things all the way until the return address, right? So instead of like, filling this part with garbage, what you can do is filling this part with your shellcode, basically, okay? So your actual shellcode is like bunch of ones and zeros. So when you're doing the buffer overflow, you're just overwriting this part with your shellcode, and then the return address should be the beginning of this shellcode, right? So the top, which is basically this return address, should be pointing to the beginning of the shell. What we usually do is that since finding the beginning of the shellcode might be something very tricky, we're kind of adding what's called a landing area, all right? So the landing area is that if this is my shellcode, in order to know exactly where my shellcode starts, I need to know the exact byte, right? So what we can do is that saying that, okay, what I'm gonna do is that I'm gonna add this landing area. And this landing area is nothing but just a bunch of no-ops. No-ops is this instruction that doesn't do anything. And what I can do is that instead of like finding the exact same location, any point in this landing area will do, right? So I'm basically just increasing the chances of finding the correct address. Because if I return to this point or this point or this point, any point in here, that would be fine, because I'm just executing some no-op instructions, and at some point I'm gonna start executing the shellcode instruction, and we're gonna be fine. And this way we kind of like increase the success rate of this attack. Otherwise, without this second part, I had to know exactly what this address is, and that's usually it's a difficult task to do. Okay. And so that's where we usually call it a no-op sled or landing area in some sense, where some part of the buffer overflow is just a bunch of no-ops, then the shellcode, then the return.
This situation, your shellcode must be less than the size of your buffer, right?
Yes, and usually that's the case because shellcode is only few lines.
Okay.
Yes.
'Cause,
That's why you
previous
really
cases-
want to do shellcode. That's one of the key reasons that you want to do shellcode. Because you cannot really run a really large program. You want to do something that is very small, and you invoke the shell, and then within your shell now you can actually jump virtually to anywhere else in your code.
I see, because in the previous example, you had overwriting past the return address and running code there, which then you could run like an arbitrarily sized program. Right?
Yes, exactly. Are we good? Okay, so how common is the buffer overflow? Unfortunately, very common. That's still a major security issue because there's many unsafe, functions and bugs that we have that could cause, buffer overflow. They actually, in the list of, most dangerous types of attacks to a system, out of bound writes, which is basically kind of like another word for buffer overflow, is number 2. So it's the second most important thing that we need to worry about. And this is 2020, just a few years ago. So it's very recent. Okay. So now let's actually talk about how do we defend. I think we don't have much time, but just very, very quickly, I'm going to talk about a few, and then the rest will be still nowhere to next week. So their defense has many different layers. You can do, of course, doing something called, safe languages, which basically eliminate the chance of having buffer overflow at all. So there are lots of, different options for safe languages. Compiler can work and help a lot. There are stack protections such as stack canaries that we're going to talk about. There is methods called control flow integrity, which again we're going to talk about as well. And then there is also other methods called data execution protection and ASLR, which are also very useful. I'm going to talk about a few of them. Let me just talk about the stack canary, and then I'm going to let you go. So the idea of the stack canary is very simple and very interesting. So the idea is that if we have our local variables here and a return address here, and then if the local variable is gonna overwrite everything, what we can do is adding this random variable, adding this random number in between, which we call the canary, and this is our local variables. So when we are doing the overwriting, what we do if we want to change the return address, and if you're going into this direction, we need to overwrite the canary as well, right? So there's no way that we cannot write the canary. And what we're going to do is that in order for the processor to know whether your stack pointer has been modified or not, all the processor needs to do is check this canary value and see whether this canary is alive or not. Which means that, let's say I'm writing a specific random value for this function foo, and I know that what random value this is. Before returning, I'm gonna just pop this value and compare it with this random value. If this is the same, it means that this value has not been overwritten. If it's not the same, it means that something has changed into my stack. So I no longer return to this function. So I stop executing it.
Can it not just rewrite the canary?
But the problem is that the attacker does not know what that random value is, right? So the random value is something local into the stack, and the attacker has no way of reading that random value. The only user that knows what this value is the actual user, actual processor.
So would it be fair to say that an attack on the random generator would be an attack on the system?
Kind, yes. There are ways of actually attacking canaries as well. I'm gonna briefly talk about the next section. But that's generally the simple idea. All right, so I'm gonna talk about the others in the next lecture.
Thank you.
That's it.
And